Hi, General Physics. Last week, I got some emails asking me to give more examples of how you can use conservation of energy to solve a problem. So what I've done is I have created two word problems that can be solved using energy. And today, we're just going to go through those two word problems. So one of the big concepts that came out of last week was this idea that energy can be conserved. So however much energy you have at the beginning of your problem should be exactly the same amount of energy that you have at the end of your problem. And the way that we can keep track of that energy is using this thing called an LOL diagram. So I have, I did this on your homework as well. I gave you guys the LOL written already, okay, and we can see that here. If we kind of trace out the two bar graphs and the O in between for our system, they spell out, LOL. And that's why we call it an LOL diagram. Now, the LOL diagram, again, is just a way for us to keep track of the energy, to make sure that we have the same number of joules at the beginning and at the end. So, what we're going to do is we're just going to look at this first example problem. From a 50-meter high platform, a 0.1 kilogram stone is thrown straight upward with an initial speed of 5 meters per second. What is its speed 10 meters above the ground? Now, we could have done this problem using stuff that you guys already know from first semester, right? We could use all of that lovely acceleration information to solve this problem, right? And I know you guys would love doing that. We'll put an exclamation point to say, oh, yes, we could solve this using acceleration. But that would involve, getting out our kinematic equations and having to do some serious algebra. And energy is just going to be a way, way easier method to solve this. So what we're going to do is we're going to start by filling in the LOL diagram just to kind of make sure we keep track of everything. And when you start an LOL, you should start by defining your system. And so we got to think, what is the stuff in the problem? Well, in the problem, we have a rock, we have a cliff, right? We have the earth in general. We always want to include the earth, right? The earth always matters. If we're on the earth, we got to include it. And I think that's about the only things that we have in this system. So let's start and think about what's going on right at the very beginning of our interest. It is right there, okay? When this thing is 50 meters above the ground, we would say that this is our initial position. So, since we're 50 meters above the ground, we know we're going to have a whole lot of gravitational energy. So, just throw in a ton. You don't have to be exact with this. It's just, there's no numbers involved in these LOLs. Just do it by feel. Now, we're also told that it is thrown straight upward with an initial speed, right? With initial speed 5 meters per second. And we know that energy of motion is kinetic energy, so we ought to have some kinetic energy. Again, it doesn't really matter how much kinetic energy we give it. We just want to acknowledge that, yes, we have kinetic energy. So that's about all the energy that we have at the initial, right? There's no spring energy here because we don't have any kind of like spring or rubber band that's being deformed. So let's now move to our final position, right there, 10 meters above the ground. And let's think about what kind of energy this stone has when it is at its final position. Now we know it's still going to be falling to the ground, so we expect that it will still have kinetic energy. And in fact, it might have a whole lot more kinetic energy, right? It's going to be moving faster when it gets close to the ground than it was way up high when we first threw it. It is still technically above the ground, right? Like we are still these 10 meters above the ground, so we are still going to have some gravitational energy as a result. Not as much gravitational energy as we did before, right? Because we are now much lower, and we are closer to our final resting place than we were previously, but it's still there. Now we do not have any spring energy because again, we don't have any springs rubber bands, and we are going to just ignore any kind of thermal energy because when we throw something up into the air, we always assume that it is frictionless. So this LOL diagram, I'm making sure that I have all of my energy accounted for. Okay, so again, I don't really care how many boxes you have, but to show that energy is conserved, we need to have the same number of boxes. We have 1, 2, 3, 4, 5. We have 6 boxes worth of energy on this side, and we have 1, 2, 3, 4, 5, 6 boxes worth of energy on this side. So fantastic. We are showing that energy is conserved. And now I can use this LOL diagram to write myself a little energy equation. And this energy equation is just going to say, it's just going to try to just re-express what I have written on the bar graph, right? And this is saying that my initial kinetic energy, right? And then I've got initial gravitational energy, right? And those are the two kinds of energy that I have at the start. And according to conservation of energy, that should be equal to my, well, what do I have at the end? Oh, I've got some kinetic energy at the end, so we'll call that final kinetic energy. And I've got some gravitational energy at the end, so we'll call that final gravitational energy. Okay, so this is my energy equation. I got kinetic and gravitational at the beginning. That should equal kinetic and gravitational at the end. And this energy equation is going to help me make this prediction, okay? Because the problem wants me to say how fast this thing is going to be moving when it gets 10 meters above the ground. So let's start filling some stuff in. And the first thing we're going to do is we're going to fill in the equations for each of these kinds of energies. So we got 1/2 mv squared to calculate kinetic energy. We got 9.8 times m times delta y for our initial gravitational energy. Right, so kinetic energy is 1/2 mv squared. And then gravitational is 9.8 times mass times your height. Okay, and even though all of these letters are exactly the same on both sides of the equal sign, one of them is, referring to the initial. I tried to color code that as red. And the other one is referring to the final. So even though it looks like all the same letters, we're going to be filling different numbers in. So don't do any canceling out. That would not be good. All right, so let's fill in all of those numbers that we are told. Okay, so we'll start with 1/2, and we're told that the mass of the stone is 0.1 kilograms. So we'll put in 0.1 kilograms. We are told that we could throw it up at 5 meters per second. Okay, and then this is going to be 9.8 times that 0.5 kilograms of mass, and this is 50 meters up in the air, right? Because at the start, right, we were way, way, way up there, 50 meters. We're going to set that equal to all the final stuff. Ooh, looks like I made a mistake. That mass was not 0.5, it was 0.1. Ooh, close one. Okay, so let's do the kinetic energy at the end. So 1/2 times 0.1 kilograms. And we don't know this V, okay? This is the thing that we are trying to find, is this V right here. So we'll just leave it as a V. And we'll add 9.8 times 0.1 kilograms times our height above the ground at the end, and that was only 10 meters, right? There it is, 10 meters right there. Okay, And so, now that I have all of these lovely numbers, I can start putting them into my calculator. Can you guys hear that calculator sound? 0.5 times 0.1 times 5 squared plus 9.8 times 0.1 times 50. Well, what do we have? On the left-hand side of the equal sign, we have 50.25. And that's joules, right? Because joules are the unit of energy. And all we've done is we've just totaled up how many joules of energy we should have. And now let's see. On the other side, 1/2 times 0.1 is 0.05. V squared. Here, you guys don't need me to tell you that this is what we're finding. Let's add 9.8 times 0.1 times 10. Well, that was just 9.8. Okay. So let's subtract 9.8. Ooh, this is joules. Minus 9.8 joules from both sides. We got 50.25 minus 9.8. That's a solid 40.45. Oh no, I'll run into my other example problem. Rats. Bad job, Fassbender. Should have spaced it out a little bit better. Well, this is the thing I love about Notability. Let's make that bad boy smaller. There we go. Okay. And so what do we have? I'll switch to black. Now that the color coding doesn't make a difference, switch to black. 40.45 joules equals 0.05 V squared. So to get the V by itself, we're going to divide by 0.05. And we get 809 is equal to V squared. So let's take the square root of that. Square root of 809. Well, that is 28.4 meters per second. So there we go. This bad boy is going to be moving at 28.4 meters per second by the time it hits, or it gets 10 meters above the ground. Yeah, we didn't have to use any kinematic equations to get that, so that was pretty awesome. Okay, so let's do another example problem. We'll move through this one more quickly because you guys get the idea of, how to use the LOL, how to write an energy equation, and then how to substitute in the individual energy calculations and solve the problem. So this is a 6 times 10 to the 5th kilogram subway train is brought to a stop from a speed of 0.5 meters per second by a in 0.4 meters by a large spring bumper at the end of this track. What is the force constant K for the spring? Okay, so let me think first about my system. So my system is going to be the train. It seems quite important. I think the spring is a big deal. After all, it's stopping the train. And of course, this is all happening on Earth. So you got to include the Earth. Now, at the beginning, right, this train is booking it. Well, not so fast. I guess it's only moving at 0.5 meters per second. So maybe it's a little bit slow, right? Maybe it only has like that much kinetic energy. Now, this train is already at its lowest position, so it doesn't have any gravitational energy. And as of right now, right, as of this very moment in time, this spring has no stretch, okay? It doesn't matter how long the actual spring is, okay? Like, I don't care about the length. The length of the spring is whatever. But how far it has stretched, no stretch. So, no spring energy. Okay, what about at the very end? What about when this train, right, it has moved along, it has compressed this spring, so now the spring is like way tiny. Well, it will no longer be moving, so no more kinetic energy. Still will be at its lowest point, so no gravitational. We don't have to worry about friction here, so really I think the only thing is that we would have spring energy. So our energy equation would say that our kinetic energy, which is the only thing we have at the initial, that must equal our spring energy at the end. All right, cool. So taking that information, right, initial kinetic energy is going to equal final spring energy. Well, the kinetic energy equation is 1/2 mv squared, and the spring energy equation, oof, I think I probably have to look at my notes to remember this one, because it's the long one. It's pretty long. It's 1/2 times the spring constant times final stretch squared minus initial stretch squared. So let's see if we have all these numbers. Do we have the mass of the train? Why, yes, we do. 6 times 10 to the 5th kilograms. Do we know how fast this train was moving? Oh, that's right. It was moving kind of slow. It was 0.5 meters per second. We square that bad boy. All right, so that equals 1/2 times our spring constant K times, let's see, the final stretch. Oh, we don't know what that is. Oh, wait, yes, we do. What am I saying? We know how far this thing got compressed. Got compressed 0.4 meters. Duh. And how compressed was it at the start? Well, it wasn't compressed, right? Right? We said no compression at the beginning. All right, cool. So the only thing that we do not know is our spring constant. That is the only unknown here. So let's put this into the calculator. 1/2 times 6 times 10 to the 5th times 0.5 squared. Looks like we have 75,000 joules of energy at the start. So we need to have 75,000 joules of energy at the end. And we shall. Okay, so 0.4 squared times 0.5 is 0.08. There we go. So let's just divide everything by 0.08. And we should get our answer. What is 75,000 divided by 0.08? Oh my goodness, it's huge. It is 9.375 times 10 to the, it looks like 5th. And the unit here would be newtons per meter. That is the unit for the spring constant, is newtons per meter. So that's our answer. 9.375 times 10 to the 5th newtons per meter. There we go. Easy peasy, lemon squeezy. Well, it's fabulous talking to you guys, and I hope that this was really helpful. Good luck retrying Unit 8 Worksheet 2 on ClassKick.